welcome everybody. Today for our tech talk, we are going to be talking about cryptocurrency. We have Luke Crouch here. He is a privacy and security engineer with Mozilla and often teaches classes for us at the library, which we super appreciate. He's also a volunteer with Techlahoma, which I'm sure he'll talk a little bit about. I'm going to record this talk and make it available on the library's YouTube channel. So I'll send that out as soon as it's available. If you've not used Zoom before, there's a chat function down at the bottom. So if you have questions, feel free to drop them in there. I will send them to Luke as we have time. And we'll also have some time for questions and answers at the end too. But thank you so much for coming today. And I think next week our talk is going to be on, I'll tell you at the end because I don't remember. So we're gonna go ahead and get started. So take it away, Luke.
Cool. Thank you. Let me make sure I'm in the right mode here. Okay, yeah, so like Caitlin said, my name is Luke. I'm a privacy and security engineer for Firefox. I am not a crypto expert or a finance expert or anything like that. So mostly what I'm going to talk about is based on my research into cryptocurrency as we've had to deal with things like cryptojacking attacks of Firefox. So I do not know everything about all the different coins or exchange rates or anything like that. I'm very much on the technical, the deep technical side. I am also a contributor and volunteer for Techlahoma. If you don't know what Techlahoma is, it is a statewide nonprofit, and our mission is to advance the technology community across the state. So we host 39 meetups every month. All those have moved virtual, I believe now. And we also had a virtual conference. We do 2 conferences every year. And we have Code for Tulsa is our civic coding brigade, if you've ever heard of that one. We also do a number of workshops for helping people learn to code and things like that. So that's sort of me and Techlahoma, and I'm going to suggest a book because, of course, it's a library talk. So this book, Bitcoin and Cryptocurrency Technologies. This is a textbook for the Princeton class on the subject, so it's a bit academic, but this one is definitely comprehensive, but still kind of broad. So a lot of what I'm going to give you comes out of this book. And one of the first things to say is that Bitcoin didn't come out of nowhere. So there's been a lot of, it felt like it came out of nowhere because it sort of was nothing, and then all of a sudden it was worth, you know, trillions of dollars or whatever. But there is history behind digital currencies and Bitcoin. The path to Bitcoin is littered with the corpses of failed attempts. So this is from the textbook. They'd have a good history of probably the 6 major attempts that there were for creating sort of online digital cash before Bitcoin. So here's a bunch of the ones that started up. eCoin and eCharge were a couple that got a little bit popular at one point. I think PayPal was in this space for a little while. So they obviously didn't do digital cash, but they're still around. So how and why did all this start? We need to talk a little bit about just finance in general to help sort of make the linkage between what Bitcoin and sort of cryptocurrency is doing. We need to understand a little bit about just currency. So in the beginning, sort of the way that people exchanged goods was just bartering. So you have some beads, I have a bowl, we exchange, that's what barter is. The problem with barter is you have to coordinate everybody of who needs what, and you have to find the right people who need the thing that you have. So then sort of the next stage of finance was credit. And this is a ledger that a authority figure like a mint or a bank or something like that would just keep track of who has credit for what. And so if you wanted to sell something to somebody, you would agree on a price. They would take, you know, whatever that price of credit out of their account and put it into somebody else's account. Now the problem with that is that obviously the same problem that we have now is that some people would overspend or they would abuse the credit system. So then sort of another mechanism for finance is just cash. And so hopefully we're all used to this. It's coins, dollars, physical things that represent sort of a different value that's a little bit more abstract. So the advantage of using cash is that you don't have to, like in a credit system, you don't have to keep track of this person paid this person, so that means that they can pay the next one and the next one and the next one. So that's great. There's also very precise values instead of sort of, you know, this bead in this bowl. The problem with cash, though, is how do you actually get a cash system up and going? So a lot of that is just to explain this talk is going to be a bit complicated, and Bitcoin is complicated, but that's because the financial problems that it solves are also complicated. And those financial problems are both online and offline. So a lot of the complications or the complexity of Bitcoin or cryptocurrency is kind of just because computers are complex and also finance is complex. So combining both of those things makes it complex. But if we look at sort of the history of finance online that we're kind of used to, a lot of us are probably used to credit card payments to websites where you want to buy something and so you use a credit card number and you punch that in and you get something. But one of the problems here, obviously, is that there are websites that have credit card numbers and then those get breached. And then those credit card numbers get out there, and if you have a credit card number, you can usually use it to spend, you know, money that is on somebody else's credit. So another thing you might be used to is some kind of intermediary payment, and this is something like PayPal. So instead of giving your credit card number to a merchant or a store, instead what you do is you have a PayPal account, and maybe only PayPal has your credit card number. If you go to check out at a store, you can click the PayPal button and PayPal will authorize the payment, and then PayPal will be the only one who keeps your credit card number and charges for it. So the thing with the intermediary payments system is that it's pretty complex. And there's major payment platforms out there. Like I mentioned, PayPal, there's also these Stripe, Square, things like that that try to simplify it. But they all charge fees. So just a second. All right, sorry. Okay, I think we're back. So people have been looking for a way to simplify online payments without having these sorts of major fees. So those are the problems. So online cash is what people have been looking for, and the advantages would give you all the advantages of sort of not having a credit system, so there's no risk of default, and there'd be no third-party fees. So if we want to talk about online cash, we're going to think a little bit about physical cash first. So physical cash is actually the kind of physical cash we're used to as a promissory note. So if you look at a dollar bill, it actually says this note is legal tender for all debts, public and private, and it literally has the signature of the US Treasurer on it. So that's sort of, this is a promissory note. I'm the Treasurer of the United States, and I promise that this note is actually legal tender for public and private commerce, right? So this is what cash actually is. So I'm going to put that in sort of this visual here to just, we're going to use this and show how this turns into, like, if you needed an online version of this, what would you need? So for digital cash, there's one thing to remember when we start talking about moving from physical cash to digital cash. And it's a pretty funny quote from the book that says, Bitcoin works better in practice than in theory. So we're going to talk a lot about theory for a while here before we get to an example of like a really bad cryptocurrency. But don't get too bogged down in the theory, because if you just think about it, it doesn't really make sense. What happened with Bitcoin was people actually started using it, and as people used it, they figured out more things about the system. So don't get too bogged down. We're going to go through a lot of theory. We're going to go through some crypto concepts and things like that. But let's not get bogged down in it. We're going to go kind of quickly through it. If you don't understand it all, that's totally fine. You can ask questions to Caitlin, and I'll try to either answer them as they're being asked, or I'll just say that, you know, that'll be more obvious later. So if we're going to get into digital cash and cryptocurrency as our digital cash, I'm gonna sort of build up to that at the top of this pyramid. So we're gonna talk about the building blocks that go up to eventually making up a cryptocurrency and Bitcoin. But we have to start with some of these things at the base. So we're gonna talk about sort of each one of these things, how they build on each other, and how eventually they give you something like Bitcoin. So if we think instead of the US Treasurer creating a note, if we think of just me, I'm just a person on the internet, and I want to say this note, this digital note, can be redeemed for $1 if you show it back to me, and then I sign it, right? So there's a bunch of problems that come in here that are the same as physical cash. So tampering, forgeries, double spends. Like tampering means in the physical cash world, someone might say the bearer of this note may redeem it for $1 million instead of one. So somebody basically, if you went to a physical dollar bill and tried to put zeros on a $1 bill, right? That's tampering with it. So in the physical world, oh wait, did I lose my, oh no, am I on the wrong slide? I don't think I'm on the wrong slide. We'll get to it in a second. So if we're gonna, in the digital world, we use crypto to make these things tamper-proof. And I wanna make a distinction here between what I'm shortening to crypto and encryption. So crypto is short for cryptography, and cryptography is not always about encrypting and decrypting secrets, which is what a lot of people think it is. The first building block that we're going to use out of the world of cryptography is called a hash function. And so this is at the base of our pyramid. And what a hash function does, it takes an input of any size, and then it does a bunch of magic, basically. And it produces some fixed size output. And it's really, really fast, even on something very big. So for example, if you took the entire Declaration of Independence and you threw it through one of these hash functions, it would take all of that and it would turn it into, you know, these 64 or 32 characters here at the bottom. I'm going to shorten that to 6 for the rest of the slides. Just know that it's usually much longer than what I'm going to show here. But if you take the Declaration and you turn it into this much smaller thing, if you take something else, so in this case, we took the Declaration of Independence, we put it through this thing and it came out to this value at the bottom. If you take my thing that I wrote out, the bearer of this note may redeem it for $1, and I signed it myself, if you put it through sort of the same process, you get a different hash at the end. And this is one of the most important things about cryptographic hash functions, is that you can take a lot of data and you run it through this process, and at the end you get basically this little hash value, but it's going to be different for every single thing that you might put through this. In the cryptography world, we also need hash functions to do a couple more things. So 2 different messages should never produce the same hash, like we just talked about. That would be what's called a hash collision. Then we also need the hash function to say, to hide the original value. So it's not feasible to find the original message if you only know the hash at the end. So if I am only given the hash at the end, I have no way of knowing what the original message was. There's another little trick here. If there's only 2 possible values, it would be sort of easy to guess them. So if you only had heads and tails and you ran them both through this thing, anytime somebody sees the end result, they know it's only one of these 2 things, then they know it's either heads or tails. So what we do there is we actually, this is, oh yeah, aside. because we're going to give you some practical advice. This is why you shouldn't reuse your passwords, because the way that online accounts store passwords is they run them through these hash functions. And so if you reuse a password or you reuse a popular password, then I can probably go look for the most popular passwords. I have your email address, and I go over to Disney Plus and I just try a bunch of them, and one of them is probably going to work. So that's just a little tip there. But to get around this problem where you would only have two possibilities, but you don't want someone to be able to see the hash and know what the original one is, you just add another little, what they call a nonce in there. So if you add just another like A on the end of it, then all of a sudden the hashes will start to be different. So that helps us, instead of having just heads is this, tails is this, we could put an A, or we could put two A's, or we could put AB on something, and we could start to hide the original value. So puzzle friendliness, we're not going to talk about this one. We don't have enough time. So one question would be, okay, that's what these things are, but where does all this stuff come from? How do computers actually use it? And so there's basically decades of cryptography study have created these open source tools and libraries that people like me, people who write software, people who write code, they use these libraries to actually do these things. And the reason someone like me always wants to use a library and not do my own crypto is because if I get something wrong, then it's probably insecure. So there's a tool called OpenSSL. I won't get into the technical details on this one. This is mostly for engineers who have to work with this. But the next thing we need to talk about, now that we have these hashes, the other things above it get a little bit easier to understand. There's hash pointers on top of a hash function. So we said that the hash function is the thing that takes some big message and squishes it down to some smaller hash of some arbitrary size. What a hash pointer does is you have that arbitrary message, but you also have a pointer back to the original plain text. So this is, where is the full plain text stored that made this hash? So something to point out here is that hash pointers means that anyone else can verify the truth of the data, the hash. So if you say, hey, here's a hash, I promise it's a hash of $1, but you don't actually show the original dollar, they can't verify that. But if you say, here's a hash of $1 and the original dollar, then they can run the same hash function and say, yes, that really is true. But that means that what we sort of lost there was that secrecy of the original message. So a hash gives us confidentiality to keep something secret, but a hash pointer is doing something different. It's not keeping this thing a secret, it's just making sure that this is true, that what you said was true, the integrity of this data, not that it's secret. Which again, one of the common misconceptions about Bitcoin or cryptocurrencies is that it has some sort of secrecy in it because it's encrypted or something. Nothing in cryptocurrencies is encrypted. It uses other cryptography, not encryption and decryption. So the next thing we need to look at is a blockchain. So this is probably getting closer to what you've actually heard of when you think about cryptocurrencies or Bitcoin. A blockchain is now that we have these hashes and we have these hash pointers, a blockchain is a linked list of these things. So what we have is we have some data and then someone has hashed it and they put a pointer back to the original data. The next piece of data at the top says there's a previous hash that I'm built on top of. And that's the chain in the blockchain. So the most important thing here is that this blockchain gives you this tamper-proof log of data. So in this case, what we're seeing here on the screen is that there was an original block that had a hash pointing to some previous block. There was some new data 2. Or I'm sorry, let's go up one. Then there was some data. Then somebody built a different block that pointed back to the previous one with that hash pointer and added some more data. And then somebody else or the same person did another block the same way. They added some more data. They pointed back to a hash of the previous data. And so what this means is if you create this linked list with these hash pointers, it means that if anyone tries to tamper with the data at any previous block, the hashes and all the future blocks will be different, and someone can catch that, right? So this is what a blockchain does, and it's sort of like the powerful thing that people like about a blockchain is it gives you this tamper-proof log of actions and activities, and you could do all kinds of tamper-proof logging of, you know, people are talking about blockchains for supply chains, so you always know nothing in the supply chain was altered on its way to the destination or whatever. Yeah, so again, if somebody has inaccurate data or adds inaccurate data or tries to tamper with data anywhere in the chain, someone who's looking at the end of the chain can always catch them. So this means we can have a tamper-proof ledger of digital dollars is sort of where we start to get in towards currency. If we're just keeping a log of certain transactions or certain activities, then those could be logs of dollars, transactions of dollars is where this is building up to. So that's how we can use cryptography to get rid of the tampering with the currency. So no one could tamper with any of these transactions without somebody else being able to catch them. Another problem we said was forgeries. So the way cash works, there's a US Treasury, it prints out money, and somebody tries to, you know, print a bunch of copies of that. So there are, in cash, there's a bunch of protections against this, just being able to sort of spin up a printer and print a bunch of dollar bills. These are basically just trying to make it so expensive to forge cash that it's not actually worth it. So digital cash forgeries would be something similar, where I would have my computer make this message that says, hey, anyone who has this message can redeem it for $1, presenting it to me, and somebody else gets that message and tries to make a bunch of copies of it. So what we need in the digital world is signatures, unforgeable signatures, kind of like the signature on a dollar bill and all of those other protections that they put on a dollar bill. So how do we make this sort of signature that I put on there sort of unforgeable, right? And of course, we're talking about cryptocurrency, so there's crypto is the answer to this. And there are cryptographic digital signatures. So this is another block. To understand sort of digital signatures, one thing we need to talk about first is what's called public key cryptography. I think I have videos in here that will not translate well over Zoom, but in public key cryptography, there's a really, really great Khan Academy course called Journey into Cryptography. So this has really, really great explanations of crypto, visualizations, all of that great stuff, and it has great stuff on public key cryptography. I'm going to skip these videos because I know they're not going to do well on Zoom. I'm going to definitely skip the math. So I think basically I have a better slide summary in a different deck. The most important thing that we get from public key cryptography is you as a person can have a public key and a secret key. And as long as you keep your secret key secret, you can give out the public key to everybody else. And what that public key lets them do is they can verify, if you have a message and you sign it with your secret key, they can verify it with your public key, and they know that it's only you were able to sign that. So that's the digital signature part we're going to get into. So digital signature, only you can sign your signature, but anyone can verify it. And that's, you would have your private key is the thing that you use to sign, and your public key is the thing that everyone else uses to verify. We also need these signatures to be, you can only attach them to a single document. So I couldn't take your signature off of some other dollar bill or whatever and put it onto something else. And so again, notice this is signing and verifying, not encrypting and decrypting. So again, there's no secrecy, encryption or decryption going on with cryptocurrencies. The cryptography here is giving us something else, not secrecy. It's basically authentication. Like, yes, this person really is the person who signed this thing. So the way to get a signature, we just need this thing called sign, and it takes a secret key in the message. And then somebody else who wants to verify has the public key and the message and the signature. And they can say, yes, this was definitely, a signature is definitely on this message using that secret key. So yeah, signature is I sign it with my secret key, and then when you receive that message along with the signature, you can use my public key, the message, and the signature and say, yes, that definitely was Luke signing that. So again, where do secret and public keys come from? From decades of cryptography. So this is built into all of these same libraries that people like me use. So what about this? Oh, so sorry. In this case, we've got, as a sender, I can give out my public key to whoever is going to receive my messages. I can sign the messages with my secret key. And then here along the bottom, that gets sent to the receiver as well. They now have the message, the signature, and my public key, and they can verify that, which means that if I have $1 and I sign it, and somebody else receives the $1 and my signature, then they can verify, yes, it's good. But if there's a forger out there who tries to take that message with some other secret key and put a signature on it, the receiver who has my public key checks it and says, no, this is somebody else. This is not Luke actually sending me this. This is somebody else sending me this. So now we have these unforgeable digital signatures. And now we have enough of this cryptography to build a really, really bad cryptocurrency. So the one in the book is a great demo name. It's called Goofy Coin. So we're gonna basically talk about the rules of Goofy Coin based on sort of the cryptography that we just talked about. So Goofy Coin starts with some designated entity like Goofy, and they can create new coins at any time, and the coins start out belonging to Goofy. And then the other rule of Goofy Coin is whoever owns a coin can transfer it to somebody else. So in the first step, Goofy creates a coin, gives it some sort of number or ID, and they make some kind of message that's basically create coin, and then the number, which coin number, and then they sign that with their secret key. So just like we were talking about, you write down a message and you sign it. Now, if Goofy wants to send coins to Alice, Goofy writes a message that just says, pay this coin ID, like number 1, to Alice. Alice, when you say you're going to pay it to Alice, we actually use Alice's public key as the address. And then Goofy signs this message with their secret key. So if Alice then wants to transfer this coin to Bob, she just starts a new message, just like Goofy did, and it says, pay coin number 1 to Bob, using Bob's public key as the address, and then Alice signs this message with her secret key. So what we have here is we have this tamper-proof ledger of digital dollars. It started with Goofy creating a coin and signing, I'm creating a coin, and then writing down a new message that says, I'm paying coin 12345 to Alice, signing that one. And at the top of that message was a pointer, a hash pointer to the message where they created the coin. So that anyone looking to see if this message of paying a coin to Alice is valid can go to the top of the message, go back to the previous one that it's pointing at and say, yep, Goofy created this coin and Goofy has signed off on it. and now Goofy is paying this coin to Alice, and everything checks out. Then the next one, Alice has this coin, and she writes down a message that says, I'm paying coin 12345 to Bob, and I'm signing it with Alice. And it's pointing back to the coin that I was paid by Goofy. So this is basically cryptocurrency, right? So the rules of Goofy coin, we just talked about. There's some entity out there, Goofy, creates new coins, and they start out belonging to Goofy, and whoever owns a coin can give it to someone else. And anyone can verify the coin ownership by following that blockchain all the way back to Goofy. So anyone looking at this last payment that went to Alice, or went to Bob from Alice, they can follow all of these links in this chain back to the original message where Goofy created the coin. And that means that everyone has followed all of the rules. So there's a problem here, which is a double spend attack. I'm trying to decide how technical we want to get on this. I haven't seen any questions flying in yet, which means everyone's just sort of distracted by kids or just completely bazonkers with this anyway. So a double spend attack would be after Alice has paid a coin to Bob, she now tries to write down another message that pays the same coin to check. So we don't really have any rules in Goofy coin that would stop this. So how would we decide which of these sort of branches is true? So what we're going to do is we're going to create a slightly modified currency called Scrooge coin, which is going to fix this problem. Scrooge coin is basically Goofy coin, but the new rules are there's this one entity, Scrooge, and they are responsible for publishing the canonical ledger of the transactions. So everyone is only going to trust the ledger that Scrooge publishes. And that means that everyone who wants to make a transaction has to broadcast their transactions to Scrooge. So Scrooge can do all of the checking and sign off on it. And then people only accept coins that are from Scrooge's public ledger. So what happens is Scrooge is going to build this blockchain to digitally sign. So now Scrooge is basically responsible for all of these, bunching up all of these messages into these blocks. And each block has transactions inside of it. And each transaction has, a transaction ID as well as like who's paying which coins to whom, and then it has that pointer back to the previous block. Now Scrooge is the final one, and then publishes this signature with the final one back out to everybody. And so again, just like Goofy coin, Scrooge coin has these create coins and these pay coins transactions that Scrooge recognizes. And so a create coin might look like this. We're in transaction, this is the first transaction ID, and the very first number down here is sort of the number of the coin is number 1, and the value is 3.2, and Scrooge is getting that one. We're also creating 1.4 coins that are going to Goofy, and then 7.1 coins that are going to Alice. Then on a pay coins, we have to say which coin are we using. So this coin says, go back to that transaction 1 and use that third coin, which was 7.1 going to Alice. And what Alice is now doing with this pay coins is paying one of them to Bob and then paying 6.1 back to herself. So this is the sort of create coins and pay coins. So this is a little more detailed than what we were talking about before, but this is actually how cryptocurrencies and Bitcoin organize these things. So at the very beginning, there's this create coins transaction that Scrooge has signed off on. Alice starts with 7.1 of these coins, and then she creates a pay coins transaction that gives 1 to Bob, and then she keeps the remainder, 6.1 for herself. And now Scrooge signs off on all of this and says, okay, this is everything here follows the rules. The coins were created correctly, and Alice is trying to pay Bob 1 coin, which she does have, and she's keeping 6.1 for herself, which she does have, so that's good. So now if Alice tries to double spend, she'll try to write down this other message that says, I'm also paying that 1 coin to Chuck and keeping 6.1 for myself. And now Scrooge catches her trying to do this because Scrooge has already confirmed and verified the transaction that she paid to Bob. And now Alice is trying to say, hey, I'm also using that same coin here, and Scrooge can catch her. So I don't think we're going to get into the public keys as identities things yet. If we want to go back to any of these, I'll wait for questions. Ooh, we get to skip a lot if we skip that. Okay. So in Scrooge coin, like I said, the public keys are the addresses that receive coins. People who have their own private keys sign off the transactions where they're sending their coins to somebody else. Everyone, including Scrooge, can verify that all these transactions are good. And then Scrooge signs that final ledger of all the transactions. So in this Scrooge coin, Scrooge is maintaining the ledger of all the transactions, and Scrooge has authority over which transactions are valid, and Scrooge creates new coins. So if you're like me, you kind of want to know, well, that sounds like a really nice setup for Scrooge. So how would we get rid of Scrooge? And if we take Scrooge out of this, then who's going to maintain the ledger of transactions, and who's going to have authority over which ones are valid, and who creates the new ones? And so now we get to coin miners. So if you've heard of Bitcoin mining or cryptocurrency mining or something like that, we have arrived at the miners are the people that replace a single person having to do this. Is now we have this sort of this entire network of people that are mining things to do it. So the coin miners are going to be the ones who are maintaining the ledger. They have authority over which ones are valid, and they can create the coins. So who are coin miners? If you look at Bitcoin specifically, Bitcoin is a peer-to-peer network. So you can actually download Bitcoin if you go to bitcoin.org, and you can run it on your computer. I promise you it'll take up all your hard drive space, so you probably don't want to do that. But you can start participating in Bitcoin just the same way that we all used to participate in Napster or whatever, where it's just peer-to-peer networks, computers talking to each other. But yeah, so to pay Bob with miners, instead of telling Scrooge, Alice would broadcast her transaction to all of the Bitcoin nodes that she knows about. So if she's running Bitcoin on her computer, she creates this transaction, and then she broadcasts it to all of the other computers that her computer knows about that are also running Bitcoin. Then Bitcoin nodes are governed by this distributed consensus protocol. I'm going to skip through some slides here because a lot of it is pretty technical. But basically, the transactions are broadcast to all these nodes instead of Scrooge. Each node gets new transactions and then organizes them in a block. And there's these rounds, and every round, a new random node gets picked to be the one to add transactions to the end of the block. And then the other nodes only accept that block if all the transactions are valid. We will skip this. There's a lot of stuff we can skip. Okay, so what we really need, all of that was basically all the bad things that you could do if you're running a node and you're malicious. What we really need in Bitcoin and cryptocurrencies, we need something that forces most of the nodes to be honest. We don't have to have all of them, we just need most of them. So how would you make a majority of the nodes, of the people that are out there running Bitcoin, behave honestly? And the answer here is not crypto, it's actually incentives. And this is especially where this quote, Bitcoin works better in practice than in theory, comes from. Because if you just look at the cryptography of Bitcoin, it doesn't make sense, it doesn't work. Like, there's no reason anyone would start this network because of all of the ways you have to try. There's no cryptographic way to make people be honest. But what the incentives are is, can we give nodes some kind of incentive to behave honestly? And we don't really know their identities. They're just running some software on a computer, so we can't really like mail them cash to behave. But if there was this digital currency that we could give them without having to know their real identities, then we could solve this problem of how do we pay honest nodes. And so this is what the Bitcoin network does, is if you are a Bitcoin miner and you create the next block and you do it in an honest way, then you get to put the create coins transaction in that block and you pay it to yourself. So this is how Bitcoin mining works. The Bitcoin miners are hearing about a bunch of transactions, they're organizing it into a block, and if they're doing it properly, then all of the other nodes agree, yes, that is the right block. You found a good block and you didn't cheat or anything like that. And the block that they created had, as the very first transaction, create coins to myself. So this is why Bitcoin miners are called miners, is because they're basically mining for these coins. They're creating the coins. They're creating the coins because they're basically maintaining the ledger and checking the ledger all the time, making sure that all the transactions are good. And when they do that and they have done it well, then at the top they get to have some coins, right? They get to create coins out of thin air. So miners would only want to include valid transactions because they want their own create coin transaction, which is the one at the top, to be included in the long-term blockchain. So again, the transactions are broadcast to everybody. Every node collects new transactions into a block, and then some random node adds it to a block at the end of the blockchain, and the other nodes only accept it if all the transactions are valid. So in each round, how do you pick a random node? So we're getting close to the end. I want to leave time for questions and for people who have to leave out at 1. So we'll do this quickly and then I'll stop. So in Bitcoin and cryptocurrencies, most of them are based on what's called a proof of work. And so proof of work is how we can sort of approximately find a random node based on something. And in Bitcoin and most cryptocurrencies, it's computing power. So nodes compete with each other on computing power. And the way they do that is with that hash puzzle thing. I skipped that before, but the hash puzzles basically say if you choose, let's go to an example of a hash puzzle. If you need to create a block, you have to find, remember we talked about if you just have these two messages, heads or tails, but you start adding characters like an A or a B or another, or 2 A's or whatever. Bitcoin requires that to create a block has to have one of those little nonces in it, like A, B, C, D. You can try trillions of them, and that's what's going on all the time. It has to have that. It has to have the previous block's hash, which is that hash pointer, and the list of all the new transactions that are going into this block. And given all of that, if you hash all of this, which is going to be what the next block points to, the hash of that needs to fall within some certain range. So you can't just hash anything and be like, oh, here it is, right? You have to find in Bitcoin, you take the sort of nonce that you had, the previous hash, and all these transactions. And in Bitcoin, it literally is, if you take a hash of this, you have to have something that starts with lots of zeros at the beginning of it. That's literally what it is in Bitcoin. So the puzzle-friendly part says that the only way you could find that is to just keep trying a bunch of random A, B, A, AC, AD, like you just try trillions of these different little things that you throw into this until you come up with one of these things that has lots of zeros in it. So this is me trying to mine a Bitcoin on my little laptop here. I tried like 12 times, right? And that's never gonna work. But I took a whole bunch of things, put them into this thing, and I got a bunch of, the first one starts with 5F, that's not gonna work. The next one starts with 47, that's not gonna work. So none of these even start with 10. If you go to blockchain.com, which let's see if I can just change my share now. Oh no, it's not on the home page anymore. Let's see, is everyone seeing this blockchain? Oh, here we go, maybe it's under data. Okay, so if you go to blockchain.com, they have this blockchain explorer. And this right here is literally the latest block that has been added to the Bitcoin blockchain. And so you can see it was May 29th at 12:43. And this was the hash. It has all of those zeros in front of it. So you can see there's all of the zeros that are in front of the hash, the date, time, and you can see the transactions. So the transaction, this is, like I said, there's that create coins. I think, yeah, newly generated coins. So this was a company called Coinbase who found this block, who mined this block. And so in exchange for doing that, they received 6.8 Bitcoins that they paid to themselves. They also include all of these other transactions that show you that this address paid 0.00457 to these two addresses, right? And then here's another transactions, here's some in there. So this block, usually blocks have many, many, many transactions on them. Let's see. Can you tell how many transactions are in it? Actually, I think the first page will tell you. Let's take off the pages. And then Caitlin, if you've gotten any questions, we can start taking questions. Yeah, there were 2,794 transactions included in this block. But we're going to stop here because we got to Bitcoin. We got to actually the latest Bitcoin that was, mined minutes ago or whatever, and all of those things that sort of built up to it. So I'm going to stop there and go back to slides and do questions. All right, Caitlin, any questions? Skip past this.
I haven't gotten any yet.
Okay.
But what types of things do people usually use Bitcoin for? What types of transactions?
So I'm going to be honest. Bitcoin is used a lot in dark markets. Because, so like I said, there's no secrecy in Bitcoin, but even as well in this blockchain explorer. Okay. Did I already close it? Oops. Here we go. So even if you're looking at the blockchain explorer, notice there's no names and addresses on here, right? There's just these really long identities. So this is an address that a Bitcoin is paid to. From here, inside the blockchain, you can't really see anything about the person who owns this. It's just showing a bunch of addresses where it looks like in previous transactions where this address paid to some others. There's also this one here where this address received some Bitcoin and that kind of thing. That does not mean Bitcoin is anonymous, because sometimes if you just punch in addresses, you can start to, so the address is in here. Sometimes you can find on websites, you can click, and some people have published their Bitcoin address on a website or something. And so if you just look up their address, you might be able to find their website, then you might be able to find their email address or something like that. But if you're using it in a way where you don't put your address on anything that's associated with you, you can use it more or less anonymously. And so it is used for a lot of things that people would rather not have associated with, than their real identity. You can just sort of imagine all of the things. It is like, even among the shady things, it's mostly in drug markets. So.
What about the economics of Bitcoin? Like, does the price fluctuate or does it stay pretty steady? Is
Yeah,
it
that's where,
the currency in that way?
yeah, so I don't follow that too much. I think it obviously went through a huge peak. There's nothing intrinsic about cryptocurrencies that makes them more or less valuable than other assets. I guess would be sort of the main takeaway for the economics part of it. So I have a degree in economics as well. And yeah, the Bitcoin is a very interesting economic mechanism in the sense that in some places the official currency is corrupt, is not valuable, suffers from huge inflation. Like it is in some places official currency is just worse, right? So in some places having something like Bitcoin or digital currency or cryptocurrency is actually like pretty economically significant, not in a sense of like, oh, it's worth a lot of US dollars, because they don't actually care that it's worth US dollars. They don't care that it's worth any of their own currency. It's just, this is a currency that is more stable for them than their official currency. So from an economic perspective, that's one of the most interesting things about digital and cryptocurrencies, is that you can basically give people an alternative currency that they can use if they have, all you have to have is a smartphone, right? You have a smartphone, you can use it, that's it. And with the amount of, not even a smartphone, I mean, you can have a feature phone and you can have a ledger, right? It can be handled in a server for you and you can just make transactions over text messages and things like that. So that's probably, from an economic standpoint, what's one of the most interesting things about Bitcoin and cryptocurrency. Not necessarily the prices. The prices will always come and go and fluctuate and things like that.
Are there any good resources for learning more about cryptocurrency and like kind of the function or how to use it practically versus the stuff behind it?
Yeah, I would say you should check out lynda.com, right? Because library still has the lynda.com arrangement. So if you don't know, lynda.com, Lynda, is a great online site, lots of resources. And if you have a library card, you get a free sort of premium lynda.com membership with your library card. So
Yeah,
you can go to Lynda and check all kinds of, they're much more, I guess, digestible, and they have a much broader variety of cryptocurrency courses.
I'll send out a link to Lynda with my email follow-up, and I also have a list of resources of library books and other courses that might be interesting for people if you are looking to learn more. But Luke, thank you so much for coming out today. Really appreciate it. Next week, our Tech Talk, I looked it up, will be on how to spot fake news. So some things that you can do to stop the spread of misinformation, and some interesting recent cases of the spread of misinformation. So it should be fun. But Luke, thank you again for coming out. As I said, I'll be sending out the recording of this talk, and if anybody has any follow-up questions, just let me know, and we will see if Luke is generous enough to answer them for you, maybe via email, especially for people who are watching the recording. But you all have a good weekend.
That's great. Thanks, you too.